So, 4.5 exponential models, practice applications of exponential functions. Learning objectives. Here you will be further explore your exponential models. So we're going to do exponential models, right? And in what, through the use of data, functions, and graphs. Data, functions, and graphs. You will be provided data from real-life situations such as population growth, compound interest, etc. A representative of exponential growth, and provide a function and graphic model to use the graphing calculator. Okay, so what's an exponential model? Exponential growth can be a bit surprising. Here's a video you can watch on that. And here are the other things we can read about. Here's some data. Now, let's use the practices. Practice here. Going back here, I defined exponential model equals y times a times r to the x minus c divided by b plus c, where d is the vertical shift, a is the first value of y output of the table, c is the first x value or input, and dx, b is the change in x, r is the common ratio. So here's we have to complete the practice on exponential functions. Here I'm going to make this table. I'm waiting for that. And again, we have here x, y, dx, or dy, dx, dy, common ratio, and model, and finally residual. And for this, we have to put some data in. In this case, in 2003, what happened? 600 million TVs were there. Now, according to this, it was projected that the amount of TVs would increase by the rate of 20% each year. Based on this model, how many TVs would there be in 2008? In millions of TVs. So let's write 2004, 2005, 2006, 2007, 2008. Now, easy enough. This would be equal, recursively defined, I'd have to say it's this one, oops, B1 divided by, or times, 20% is 1 plus 20.0 divided by 100. You could also try your hand at just dividing it yourself in your mind. With the decimal over two places, that's 1 plus 0.20, that's 20%. Same number. Okay, now what you want to do is press Control, click, and fill it out to the time you want. And there you go. It's 1,492.93, 1493, I would say, to the nearest, round to the nearest million. So that's 1492, and change it to a 3 because this 9 is bigger than 5. The first 9 after the decimal. 1493, and check it. Good. Okay, here's another situation. But before I do that, let's remind you all that you can do delta list, spelled out, of the y's. To notice that it's not linear, equals delta list of the inputs, which is column A. And let's check out the rest of the formulas here. Supposed to get the change in the change of the y, which equals delta list of column C, where I put the y's. If those are constant, be quadratic, it isn't. And then common ratio, don't put anything here because we do this recursively, just like, but if it's exponential, you know that it would equal, well, would equal B2 divided by B1 times 1.0 to get into decimal. Then click on it, Control click, and fill it. And you would end up high with the common ratio of 1.2. Now that I know that's 1.2, again, I can go with the model, which we had said could add a note to explain it. We could say it's the first Y. The first output was how many? It was how many TVs was it? 300 million times 1.2 raised to the A minus the first year, which was 2003, I believe, divided by the change in the years. In this case, it's 1 to divide by nothing, press enter, and that should match my output. But it wasn't 300, it was 600, and it was 2003. So it's okay. It was 600 I started with. So 600. And now, yeah, that's 720. Now to check without having to scroll over, I'm going to define residual as the difference, what's left over from my model minus my data, G minus B. And there's no difference because basically I used 2 points to model this, 600, 2003, 600, 2004, 720, and just repeat the pattern. So of course it's a perfect match. Okay. Why? Oh, A to the B. So this would be 7. Now let's use a sketch pad. What am I doing? It's 10 to the negative 4. I mean, 10 to the 3. 10 to the negative 4. But this really equals 10 to the 3 times 10 to the 4, which in turn equals 10 to the 3 plus 4, which equals 10 to the 7. Let's see if it works out. 7. 10 to the 6. I'll leave it